Well, we will continue our lecture on biochemical reaction engineering. So I'll explain here typical process of biochemical engineering, and let this is sterile medium reservoir. Indeed, we will need air, so this will be air filter to ensure only clean air put. So after this, here we have a valve. Then we will have a rotary for controlling the flow rate. Then we will go to a pump, which also pump the reservoir content to a reactor, which contains a mixer. Here we have air spurger, which also connect to an air filter, also with a rotometer, and then also this is compressed air. Here also we have a controller for pH, which is pH meter, and this will gives inside to a container, which will be pump either AOH or HCl in order to control the pH in the medium. Here we have a pour sample for taking sample of the reaction mixture. So we need to control several volume, need to control pH and temperature and dissolve oxygen. Also we need to sterilize the medium. So what we need know something about oxygen transfer rate, which is known as OTR. We can imagine here a gas, and here we have a liquid. So concentration of dissolved oxygen here, which will be C star, and drop to Cl, which is concentration in the liquid both. So oxygen transfer rate will be equal to Kl multiplied by A multiplied by C star minus Cl. We know that oxygen transfer rate here is milligram O2 divided by liter hour, and Kl is oxygen transfer coefficient in centimeter per hour. A here is interfacial area, centimeter or 2 per centimeter cube, and C star is saturated dissolved oxygen, and Cl is dissolved oxygen concentration, which is in milligram per liter or gram per liter. Both Kl multiplied by A will give oxygen transfer coefficient its unit is 1 per hour, similar to K in chemical reaction for ferrous order. So oxygen transfer rate is rate limiting step, and we know that from gas to liquid, oxygen transfer from here will be uptaken by microorganisms in the liquid both. So we need to put oxygen transfer rate must equal to oxygen uptake rate, and this is KLA C star minus C liquid must equal to oxygen uptake, which is mu multiplied by X over yield of X over O2. Here yield meaning the yield of cells according to oxygen consumed. So yield X over O2 multiplied KLA C star minus C liquid must equal the change in cells over dt. So yield X over O2 multiplied by oxygen transfer rate will give us cell growth rate. Now let us see we know that Michaelis Menten theory or kinetics, if we assume that a single enzyme system is responsible for uptake of substrate S, and S here is limiting, we know that we could have S1, S2, S3, and this means several substrate. We have to choose S as limiting step, which is the lowest step to control the reaction. We know that according to this, mu will be equal to mu max multiplied by S over Ks plus S. And if we represent that in this figure, this will be S and this will be mu. We expect that we have just like that shape, and this is mu max. We know that when we have a half mu max, we can put it and compute this S as equal to Ks. So Ks here is saturation constant, in gram per liter, and the mu here is a specific growth rate, in 1 per hour. So we now try to make for batch culture growth model, and we need to express X, which is number of cell, as a function of T. And how we will do that? We know that specific growth rate, the mu, will equal to 1 over X dx over dt. That must equal mu max S over Ks plus S, and this equation 1. Also we know that X minus X naught will be equal to Y X over S, this is yield, multiplied by S minus S naught, or we can solve for S as this. S will be equal S naught plus X naught over yield X over S minus X over yield X over S, and this will be equation 2. Here yield X over S is cell mass yield, If we combine equation 1 and equation 2, we will get dx over dt will be equal to mu max s naught yx over s plus x naught minus x divided over ks yx over s plus s naught yx over s plus x naught minus x multiplied by x at t equals 0, x equal x naught, and that will give us an equation which known as Logistic Equation, which is as follows: ks yx over s plus s naught yx over s plus x naught divided by s naught yx over s plus x naught. This will be ln x over x naught minus ks yx over s over s naught yx over s plus x naught ln s naught yx over s plus x naught minus x multiplied by syx over s, and this will be can represent it as a graph here, and this will be x with time. Now we need to know how to determine kinetic parameter, which is ks and mu max. So we know that specific growth rate is equal 1 over x dx over dt, and by separation of variable we will get mu t equal to ln x over x naught. If we represent this by graph, it will be gives a straight line with a slope equal to mu max, and this is t, and this is ln x over x naught. So we can compute here the kinetic parameter, and we have to require some data or variable data, especially at low concentration of S. So in chemostat we have to evaluate ks and the mu max and yx over s and other system parameter. Also we have to study the change in environmental affection or will affect the cell physiology. Also we have to select for cell with designed metabolic capabilities according to process requirement. If we have to design a system for degrade toxic compounds, we have to choose a cell capable of degrade these toxins. Now for second order or for continuous stirred tank reactor, which is also known as chemostat, we have to describe the dynamics of cell growth, substrate, and the product formation. So if we have CSTR here, this is our mixing. Indeed we have input and we have output, and this is VR, which also represent as liquid volume. not the entire volume of the reactor. Here we have gas asperger or air asperger. So we have here F, we have S naught, we have X naught, we have P naught. So F here is flow rate in liter per hour. S naught is number of cells or substrate initially. X naught is denote to cells and P naught denotes to product. So here we will have F, we will have S, we will have X, we will have P. So we need to control this bioreactor, and we need to describe the dynamic of cell growth rate. Here X will be start to growth and multiplied to give final cell, and we have also to denote substrate utilization. So if we this is S naught will decrease because it is substrate. Here X naught start from 0 and start to increase. This is number of cell. At the same time, I expect there is our product increase during the reaction. So if we make a mole balance for this reaction, we will get Fx naught minus Fx plus working volume multiplied by mu x minus working volume Kd x will be equal to Vr dx over dt. Kd here denotes the disappearance of cells due to formation of toxic in the reactor or due to lack of substrate, and for this case, as we work steady state, so everything denoted T will equal to 0, and assume that Kd equal to 0, and that will give us Fx will be equal to Vr mu x. If we divide by Vr, so F over Vr x will be Vr over Vr mu x. If we defined D is dilution rate equal F over Vr, so this equation will be dx equal mu x, and so we will get that D equal to mu. Also we know that mu equal to mu max S over Ks plus S, and that will be equal to D. So we'll try to solve for S. This will give us Ks D plus S D equal mu max S, and we will have KSD equal mu max S minus SD. So KSD will be equal mu max minus D S. So we'll have S equal to KSD over mu max minus D, and this is our substrate during the reaction or biochemical reaction. Now we want to know what we called washout of CSTR. We know that X equal to Y X over S multiplied by S naught minus S. And here, this is equation 3. We can't put equation 3 into this equation. So X will be yield X over S multiplied S naught minus KSD over mu max minus D. You know that at x equals 0, dWo will equal to D. So for this equation, it will be the 0 equal yx over s naught minus KSD washout over mu max minus D washout. So we will solve for D washout. We will get D washout will equal to mu max S naught over Ks plus S naught, and here this is our upper limit for D, and D must equal or less than this Now, if we work at condition where KD does not equal to 0, so we will have Fx equal Vr mu x minus Vr KD x, and from this x with x, so F will be equal to Vr mu minus KD, so divided by Vr, that will give us D equal to mu minus KD. So we go back to our equation. It was that mu equal to mu max S over Ks plus S, that will give equal to D plus KD. We know that from this equation, if we have to know D, or we have to mu will be no more than D plus KD, and so here D plus KD. If we solve according to S will be Ks D plus KD over mu max minus D minus KD, and this is substrate when KD is not. We clearly can show that S is higher at KD does not equal to 0, which that means consuming of KD or substrate. If we check how X affected by D, we know to show that how X affected by dilution rate. We need to do a material balance for S. So we have Fs naught, which is input, minus Fs, which is output, minus Vr mu x. This is here consuming substrate by cells, minus Vr Q P 1 over Y P over S, and that will equal to Vr ds over dt. Here we have S naught, and S is the inlet and outlet concentration in gram per liter, and here we have here we have 1 over y x over sm. Y over x over sm is the maximum cell yield coefficient in gram cell per gram substrate. So this will be gram cell per gram substrate, and y over y p over s, this is yield according to product, and we will, this is product yield coefficient, which is gram product over gram subset rate, and the QP here is a specific rate of extracellular product formation. This is a gram product of a gram cell multiplied by hour. Now also we have ds over dt equal to 0. We can assume kd equal to 0, and we can assume qp equal to 0. That will give x as y maximum x over s naught minus s, or x will be equal y max x over s naught minus, we have to replace s by ksd over mu max minus d, and this is our equation here. X related with subset rate and x over s. Also we can work if kd does not equal to 0, and that will give d s naught minus s over x minus d plus kd over y max x over s, and this is to equal to 0. By replace or rearrange this equation, we get d over y x over s ap, and this is for a product, minus d over y max x over s minus kd over y max x over s, and that will give 0. If we also represent that, will give us a straight line. This is y of x over a ap, and this is 1 over d. We have a straight line, and we can making a slope or intercept to find the kinetics parameter. I think this is enough for this lecture, and we will continue on the next lecture.